In heavy industrial environments, continuous kinetic force stresses every machine component. Under constant vibration, the threads of standard screws gradually lose their grip. The micro-movements slowly rotate the fastener, causing it to back out of its housing over time. This graphic shows exactly how a standard screw separates under constant vibration, while a push-lock fastener holds the metal plates tightly together. Once a single screw loosens, the problems multiply. You get rattling access panels, compromised environmental seals, and eventually total mechanical failure. Then there's the maintenance reality of lost parts. As we see in this diagram, a standard screw falls away when unthreaded. A push-lock fastener stays captured directly in the panel, eliminating dropped hardware during routine checks. Relying on traditional threaded hardware to secure dynamic enclosures introduces unnecessary risk. High-vibration environments require a deliberate upgrade to captive, vibration-resistant mechanisms. The push-lock fastener solves these vibration issues entirely. Instead of relying on a threaded grip that can slowly unwind, it uses an internal cam-lock system. Once engaged, rotational force simply has no effect on the locking mechanism. This side-by-side comparison shows the operational speed advantage. A single push replaces the repetitive process of unthreading and rethreading, cutting maintenance access time to a fraction of a second. Upgrading to a push lock is the easy part. The real engineering challenge is selecting the right variant. Pick the wrong subtype and you might severely limit your internal enclosure space, or watch the fastener fail completely in a harsh outdoor climate. You cannot base this specification on what looks best. Choosing a push lock requires balancing spatial footprints, environmental durability, and the exact accessibility requirements of your technicians. The first constraint to evaluate is the exterior profile of the panel. You have to weigh the risk of snagging against the need for immediate toolless entry. A standard button-type fastener protrudes slightly from the surface. That elevated profile means technicians can instantly locate and operate the lock with bare hands. We can see the contrast here in this flat design comparison. Models like the 251F or 151F sit completely flush with the surrounding metal when locked. That flat exterior removes any protruding geometry that could snag passing cables, employee clothing, or moving machinery. But that smooth profile carries an operational penalty. As shown in this illustration, releasing a flush fastener requires the technician to use a dedicated pointed object to depress the central pin. Specifying a flush fastener strictly to achieve a clean aesthetic design creates a barrier to entry. In an emergency scenario, requiring an extra tool to open a panel will slow down your response time. Beyond the exterior face, we have to account for what happens inside the enclosure. The socket mechanism of a standard push lock extends inward. In tight configurations, that hardware can physically interfere with internal wiring routes or delicate circuit boards. To solve this, we use the 252FT short mini type. Its reduced socket depth reclaims that vital internal volume. This chart maps our choices, plotting internal clearance on the x-axis against environmental durability on the y-axis. The 252FT lands firmly in the high clearance zone, but because it relies on a resin construction, it stays lower on the durability scale. That tiny footprint makes the 252FT perfect for dense server racks or compact internal chassis builds. However, that exact same resin housing means it cannot survive heavy impacts or direct outdoor exposure. When an application is exposed to corrosive saltwater spray or regular physical impacts, resin components will quickly degrade. For those heavy-duty applications, the 152FT Mini Flush variant provides a distinct counter-option. Its stainless steel construction guarantees longevity against rust and physical wear, though it noticeably increases overall weight and unit price. Returning to our chart, the 152FT takes the apex of environmental durability, handling extreme conditions while maintaining a moderate internal footprint. In situations where connection security must be absolute, we look to a specialized variant like the 149FN push-turn fastener. Its mechanism requires two specific actions. You push the pin straight in to lock it, but releasing it demands a deliberate 90-degree rotation of the head with a screwdriver. It cannot pop open by accident. However, this model carries a strict engineering limitation. Its specific cam structure means it is rated exclusively for horizontal applications. When you are dealing with corrosive environments, exact load directions, or heavy security needs, Those physical and functional limitations dictate your parts list. Aesthetic preferences have to step aside. Making the final specification is a matter of running your project through a strict hierarchy of constraints. This flowchart illustrates the path. The first node asks the ultimate veto question. Is the panel exposed to corrosive elements? If your enclosure is going outside or facing harsh chemicals, the 152FT stainless steel model is mandatory. Your decision process effectively ends right there. If the environment is benign, the chart expands to the second filter. Is internal space severely limited? Taking this route solves your volume issues with the 252FT, but you accept the physical limits of a resin body.
If you have adequate internal space, you reach the final filter. Is snag prevention your top priority? A yes routes you to flush designs, while a no allows for standard, quick-access button models. Space premiums require resin. Harsh environments demand stainless steel. High-traffic, hazardous areas necessitate flush designs. The push lock category is diverse. Assuming you can standardize a single fastener type across a complex multi-panel project is a fast track to engineering failures. Evaluate your enclosures individually. Let the rigid physical realities of your hardware, the environment, and your maintenance team dictate the exact specification.
Complete